Hi, everyone. Thanks for joining us today. This is our final Break the Ice Challenge webinar. As we all know, the submission deadline is fast approaching, and we wanted to use this time to allow us to gather one final time, reiterate some of the overall themes and important items that you all will need for your submission and to be compliant and eligible to compete in this challenge. And we'll also hear from two of our subject matter experts, Jerry Sanders from NASA and Phil Newman from Anglo American. As I mentioned, we'd like to share some overall updates and announcements, along with providing some of the submission reminders in terms of the eligibility requirements and the submission elements that you all will need to provide us if you want to compete in this challenge. We'll also be providing some subject matter expertise from Jerry and Phil, and then we'll allow for a Q&A and wrap up this webinar. Without further ado, as I mentioned, the challenge submission deadline is coming up on June 18th. And many of you hopefully have already registered on the challenge website at breaktheicechallenge.com. If you haven't done so, I would encourage you to do so as soon as you can. Once you've done that, we need you to provide us your eligibility requirements form. This is provided and downloadable on the challenge website. We've received several of these in the past several weeks, and we greatly do appreciate that. However, you do have until June 18th to submit this. However, if you are able to do it earlier, we're able to let you know if you are compliant or not before you actually submit your challenge submission. And please make sure to send these to admin@breaktheicechallenge.com. Here's an overview of the challenge submission elements. We've received several really good questions about many of these. If you do have any questions, please feel free to reach out to that email address, or you can submit a question through the challenge website itself. There are many really good resources that can help you prepare your submission for this challenge. Previous webinars and 2 tutorials on submission elements can be found on the challenge website under the media and resources section. There are also many FAQs that can help you get some clarity on many questions or areas that you might be unsure of. So before submitting any questions that we would need to respond to, please check out the FAQs. Once again, the challenge submission deadline is fast approaching. It's on June 18th, so that's 10 days away. I would like to note, however, that because this is a global challenge, the specific time in which you would need to submit your concept is around 7 a.m. on the morning of June 19th Eastern Time. However, I would like to note that if you do plan on submitting your concept that close to the deadline, we cannot guarantee that we'll receive it immediately, and you'll be risking some potential IT congestion. So please try to submit this beforehand, before the June 18th deadline if possible. Without further ado, I'd like to pass it along to our first subject matter expert, Jerry Sanders.
Thank you, Adam, and I'd like to thank you and the organizers for letting me talk today about NASA's perspective of the Break the Ice Lunar Challenge and how it fits into NASA's plans for exploring the moon and potentially utilizing its resources there. So next chart. So to begin with, before diving into it a little bit, I want to remind everybody as to why we explore space and how it's evolved over time. So when you think about it from the beginning, the reasons were things like, hey, it's what humans do. We go to the North and South Pole, we climb the Himalayas. So, the moon was a challenge. Along the way, national pride and international prestige obviously jumped into the game when we started talking about space and the space race. As the Apollo program and as the space race continued, we started to recognize scientific advancements and technology advancements and new insights about the Earth and the galaxies and such. As time went on even further, we started to think about international cooperation and global partnerships, that no single nation could do it all on its own. And the International Space Station, for example, brought together countries that were traditionally adversarial in nature, for example. As we've progressed, and in the background, there's always been the thought about security and the long-term survival of human species. But in particular, two really important aspects have come to bear over the last decade in particular. One is, how do we use space to stimulate the economic development and expansion of our economy, as well as how do we make life better on Earth? So when you go to the next chart, you'll see that a main driver for NASA's work has been Space Policy Directive 1, for example, Reinvigorating America's Human Space Exploration Program. And here it basically calls out that we are going to explore the moon and go back to Mars or go to Mars and such, not just as a government, but with commercial and international partners. And with the ability to bring back to Earth, new knowledge and opportunities. Next chart. So not only why we explore space has evolved, but also how. So again, going back to the beginning of space exploration and launch vehicles, it was pretty much government led and funded. As time has gone on, though, we have started to recognize more and more that, commercial industry can bring things to bear, could potentially open up competition, which reduces costs. And we've seen that as time has progressed with the International Space Station, starting with cargo delivery, now crew delivery to the space station through SpaceX and hopefully Boeing soon. And then, habitats and satellite servicing are also starting to come into play. These are efforts that are for the government, but in partnership with private industry. That said, there's also now partnerships going beyond low Earth orbit in terms of the CLPS commercial lunar payload services missions. 6, I believe, have been selected for launch as early as this year. And the Human Lunar Services Lunar Lander Program also just selected SpaceX, for example. And we can foresee things like propellant depots and mining falling into that category downstream. But even outside of the government, there are commercial-led activities that, suborbital tourism. Blue Origin will be flying July 20th for its first mission. And we see SpaceX and other companies doing very interesting commercial-led efforts. Next chart. So when we think about, let me see, please go on. So when we think about space resources and is one of those activities that's evolved over time. Instead of taking everything with us to space like we have for the Apollo program, the shuttle program, and most of the space station program, we're now talking about using resources and making it there versus taking everything with you. Starting with finding those resources such as lunar waters and minerals and mining them, or digging up the regolith and extracting oxygen and metals, using these materials for constructing habitats and berms or making items, but also using biological aspects as well as recycling instead of bringing everything with us from the beginning. Next chart. And so when you think of this overall strategy, the Break the Ice Lunar Challenge falls really nicely into that first area. Next chart. So a big question, why would we use space resources instead of bringing everything with us? Well, the first one is that it can help reduce mission mass and architecture mass and costs. And for every kilogram you land on the lunar surface, if you work backwards in terms of the propellant needed, then the dry mass and the staging, it equates to basically over 10 kilograms or more needed to be launched into space. So if I'm making 30 metric tons of propellant to get off the lunar surface and back to Earth, you multiply that by 10, that's 300 metric tons of payload you don't have to launch into space. That could be 1 or 2 heavy lift launch vehicles. So you're reducing the number of launches, you're reducing the cost, you're reducing the risk of having to have all these missions be successful. Making things also gives the crew aspect safety and mission success. So if something goes wrong, you have the ability to correct it versus waiting. The space station is pretty close to Earth, but it takes at least 3 days to get to the moon, assuming you have a vehicle on the launch pad, and it takes 6 to 8 months minimum to get to Mars once every 2 years. So you really need to start thinking about self-sufficiency. And by being able to make things versus take everything, you can open up the possibilities of enhancing or enabling new mission capabilities. And what we learn in space can be used directly to help us on Earth in terms of recycling, clean mining, clean energy, and such. Next chart. Very quickly, when you think about space resources, at least the natural ones, water, oxygen, carbon, and metals are the most important ones that come to bear when you start thinking about crew and propulsion and making things. And if we look at the different destinations that we might be interested in going, you'll find that each one of them has, to some extent, some level of those resources. The moon is pretty poor in carbon for the most part, but we may get lucky that besides water, there may be carbon sources in the permanently shadowed craters that could be used for making different fuels and plastics and such. Next chart. Now, what we know about water on the moon is still pretty unsure. We have global measurements looking down at the surface and a little bit of the subsurface. And we have one impact in a permanently shadowed crater that showed that there was something on the order of about 5 weight% water, plus or minus, 2 or so. But how it's formed and its density and such is still a subject of debate. There are different theories, and here's an example of 4 different possibilities that are under consideration. For this particular challenge, we think that the bulk water up to 5 weight%, maybe a little bit more, with near the surface, couple of meters, with possibly a desiccated layer on the surface is the most likely form of water that we'll come across. Next chart. And then when we think about mining the water, a lot deals with where we think it might be located. Again, there's a lot of uncertainty as to where these resources might exist. The larger the crater, the better the data we have. Craters such as that very large crater in the top left-hand corner, Shackleton, that's something like 20 kilometers wide and 3 or 4 kilometers deep. Not something that you probably will want to mine off from the beginning. So we looked at a location near Shackleton off to the left And zooming in, we found a reasonably large permanently shadowed crater on the order of maybe a couple kilometers. And we found nearby areas where we might set up a base, Artemis 001, and where we might set up a processing unit that had lots of sunlight nearby, such that we could potentially mine in the permanently shadowed crater and remove the water up to that processing site. So when you go to the next chart, you kind of see what at least this one approach might entail, where you have mining operations, you're digging material up, you're bringing it to a central processing unit, it's processing the icy regolith and putting the water directly into basically a tanker that, something on the order of once a week drives out, delivers the water to the processing plant above in the sunlight, and then goes back in for more water. And please note that the slope of that is supposed to be less than 20 degrees, so it's artistic license here. Next chart. And again, this is just one option. So the other thing we need to look at is, where do we see this kind of production? What are the markets? And if you look all the way to the right-hand side, there's huge commercial cislunar activities with transportation and sending humans to Mars with lunar oxygen and hydrogen and such. Those are the long-term visions, and we're talking hundreds to thousands of metric tons of product. More realistically, when we had a supply and demand workshop recently and asked different companies early on maybe what type of propulsion systems would use their lunar oxygen or oxygen and hydrogen from water, we started to see somewhere in the order of 10 to say 50 metric tons per mission. And so initially 1 mission per year, and then going on to more missions per year gives us an idea of what type of initial production rate we would be looking at. And so what NASA and in particular the Space Technology Mission Directorate has been doing is looking at what type of demonstration missions could we perform and what kind of what we'll call a pilot plant, an end-to-end demo to reduce the risk of this full-scale plant might be. And that's in about the metric ton range. Next chart. So the strategy that we've taken to develop ISRU as part of the Artemis program is to obviously maximize ground development and use flight missions, demonstrations, and such to obtain critical information and to eliminate risk for future commercial activities. So step one, know the customer and their needs. And that last chart kind of gives you an example of what those needs might be. Step two is start the development of on the ground of the hardware and systems. And so doing in both step one and step two, engage industry, academia, and the public to the maximum extent possible. So we've used the Lunar Surface Innovation Consortium as a way of doing this. We're using, centennial challenges like Break the Ice Lunar Challenge to do these things, leading to potentially these small commercial lunar payload service or CLPS precursor missions to obtain more information about, the water in the permanently shadowed craters and how these technologies perform in the actual environment. We use the pilot plant to demonstrate the end-to-end processing, the product that is created and how good it is, and potentially using that. And all of these things need to be demonstrated on the moon before we can actually put it into a critical mission. So by doing these demonstrations, these challenges, and these missions, we're trying to break that chicken and the egg cycle of to show that we can make these and have it ready for the market. Next chart. So as I mentioned, university and public involvement is very important. We do this through centennial challenges like Break the Ice Challenge. We also use university challenges such as the Big Ideas Challenge, which had a challenge looking into permanently shadowed regions. There's an ongoing dust challenge, and we have specific university challenges like the Moon Mars Ice Challenge and the Lunabotics robotic mining competition. Next chart. If you hadn't realized, a lot of this has already started. So besides the Lunar Reconnaissance Orbiter that's been in lunar orbit for the last decade or more, 2009, as I mentioned, there are 6 surface missions that have been selected, 2 of which are specifically aimed at trying to better understand what's in the permanently shadowed craters, RIME-1 and VIPER. VIPER is a rover that will carry instruments into a permanently shadowed crater. And besides the Lunar Reconnaissance Orbiter, we have several orbital missions that are planning to be flown in the near term. On the first Artemis 1 heavy lift launch vehicle, we have 3 CubeSats specifically aimed at looking into permanently shadowed craters. The first Korean orbiter will include a camera from NASA called ShadowCam, and a science mission called Lunar Trailblazer will pick up where the M-cubed instrument on Chandrayaan left off. Next chart. This is a little bit more information about RIME-1 and VIPER and what it entails. Again, VIPER will include a drill, a mass spectrometer, a near-infrared spectrometer, and a neutron spectrometer. And RIME-1 will fly a year in advance to demonstrate both the auger drill and the mass spectrometer to prove out their performance. Next chart. And I believe this is my last one. So we have an evolving strategy for missions. I've mentioned the ground development, these first 2 prospecting missions, but we have a series of missions, and for some reason this chart's lost a lot of the pictures, that deal with excavation, ice mining, oxygen extraction, construction, all leading to pilot operations downstream. And with that, towards the end of the 2020s, 2029, 2030 timeframe. And with that, I think I'm done. Check the next chart. So, yep, thank you very much.
Thanks, Jerry. Now we'll pass it along to Phil Newman.
Yeah, thanks very much. Thanks again, Jerry. Great presentation. So I'm going to talk about, if only we were on Earth. I mean, because if only we were on Earth and we look at this challenge, I'm just going to give it from a perspective of a terrestrial miner, and what we're trying to do actually is kind of really easy. But of course, you've got a lot of challenges that you have to overcome. But let's just talk about some of the issues that we have when we're looking at mining on Earth. Next slide, please. So one of the things that we always work very hard to understand on Earth is understand actually what we're going to mine. And that's probably your biggest risk mining on Earth, and it's almost certainly the biggest risk here when we're mining on the Moon. And there's an example there on the left of the Quellaveco mine in Peru, which is a copper project that we're in the process of building at the moment. We should be commissioning it towards middle end of next year. We actually acquired it in 1992. It was actually discovered in the 1960s. We acquired it in 1992. We really spent a lot of time exploring and finalizing and understanding the ore body, and we kind of started the construction in 2018, and we should be, like I said, hitting production in 2022. So we have taken a long time to understand that ore body as best we can before we actually started excavating any rock at all to expose that ore body. And the cost, $5.3 billion. And one of the things that we have on mining is that we have resource uncertainty, which leads us to more investigation, which requires more investment, and quite often our operations are remote and far away from infrastructure, and therefore has significant other costs. When you think about that $5.3 billion cost there, about $1 billion of that only is actually the cost of the mine and the concentrator. The rest of it is infrastructure and putting things in place to allow us to actually do the mine. Next slide, please. So what do we have on the Moon? Well, Jerry's already shown us what we have on the Moon. And one of the things that points out to me when I look at that from a terrestrial perspective, I thought, wow, that's fantastic. We've got the mine, the plant, and the port, or launch pad, as it were. we've got them all really close to each other. And that's fantastic, because when we think about some of our operations here on Earth, we have an iron ore mine in Brazil where we have a 650-kilometer pipeline to take our slurry from plant to port. For our Los Bronces mining, copper mine in Chile, we have a 56-kilometer pipeline that takes the slurried ore from the mine to the concentrator. So we've got logistical issues, and logistical issues remain one of our biggest constraints to continue to exploit resources on planet Earth. When we look at what we have on the moon, we have mobile equipment perhaps best suited given the length and the capacity of the transport routes. Next slide, please. And the mining conditions. Well, the mining conditions are a dream. They're a dream. We're looking at relatively low strength material. We're not going to be mining very deep, but what is the angle of repose of that material? And when you read through and understand some of the constraints that you have when you're dealing with regolith, and I'm not an expert whatsoever, and what I read just scares me, okay? And you understand about how this material, this dusty material, highly abrasive, and travels an awful long way in that vacuum that we have to deal with on planet Moon. Next slide, please. When it comes to the mining itself, swarm robotics is going to be obviously the way you're going to go forward. You're going to use robotic methods to move material around, and I can tell you that that is already here on Earth. And this is a sketch of an underground robotic miner that we're developing at one of our underground platinum mines. And this technology is being tested in tough conditions here on planet Earth, and we'll have to see what you guys come up with in terms of developing similar sorts of technology to do the job on the moon. Next slide, please. From a processing perspective, your product here is 5 to 10%. That's what you're looking at, your high-grade product, your high-grade ice product. On planet Earth, we tend to exploit hydrophobicity of our target material and use gravity flotation. But those methods are not going to be available. We don't need to grind the material, it's already ground. We don't need to float, and luckily just as well, because obviously we can't. And we need to try and work out, and you guys need to look at ways in which you're going to extract the ice from that regolith. Next slide, please. The thing that one of the biggest hot topics on planet Earth is tailings, is the waste product. We're mining large quantities of material, millions of tons a year at grades of less than 1%. And so when the process is over, we're left with almost all that material as a fine slurry. Moon mining is going to generate waste too. You can do the maths quite quickly. If you're looking for 1,000 kilos of material at 5 to 10%, you're looking at 100,000 tons, or 10,000 to 50,000, 10,000 to 20,000 tons of waste material that you're going to have to move around. And moving material around is going to be a challenge. Next slide, please. So if I was doing this on Earth, and I really don't understand the regolith properties, but you're looking at that load and haul, one excavator, one truck. You'd looking at to heat and condense that material, send your water to electrolysis, and potentially backhaul the waste. So from the perspective of a starting point of how you would do it on Earth, that's what you would do. It's very, very, very simple. And then you'd have to pile on all your constraints. And I'm sure you've all been looking at that and assessing that over the last few weeks and months. Next slide, please. So these slides are from Jose. Jose is not able to join us, so I'll just go through them, and it's just talking a little bit more about some of the technical properties of that material. And I think one of the things when you think about the regolith and you think about that slide picture on the left there, and looking at the density and thinking about the deposit characteristics, and it's extremely fine material, which is great in terms of being able to dig it up. It's quite easy to dig it up and move it around. But in terms of the impact of that material on the robustness of your equipment, I think you mustn't underestimate the effect that that material is going to have on your equipment. I'm looking at the moment at some robotic work that we're looking at an underground polyhalite mine, which is going to be dry, but it's going to be extremely dusty. And it's a real challenge for us to develop the sensors that will look through the dust and to develop the ability to be able to get accurate understanding about what's happening around us in those sort of mining conditions. Next slide, please. In terms of the operating conditions, that dust, electrically charged, ionic dust, chemically reactive, we've got the hard vacuum, we've got the temperature, we've got the little or no gravity, electrostatic effects, and the micrometeorite impacts. A real true challenge and a fantastic, exciting opportunity for all of you to really get your teeth into this problem. Next slide, please. Jose went a little bit further and actually went and tried to split up the production cycle and kind of went into a little bit more detail than I did in my Truxcavator approach. And Jerry's not that far away from it with his robot feeding the water tankers. But let's just go through some of these sections here. So let's look at the first slide. We go to the next slide, please. The excavation loading, and I think that Jose is interesting here because next slide, thank you. Because he's referenced some silica sand mining, which is probably going to be as close on planet Earth as you're going to get to this sort of environment. Obviously, you're not going to have those water puddles that you've got right in front of you there, and nor are you going to have that size of equipment. But one of the interesting things he talks about here is the possibility of hard pans that exist within the silica sand mining operations and exploitations. And that may well be a similar sort of problem that you might find in the regolith as well. From a transportation perspective, next slide, please, Adam. From a transportation perspective, I think that everyone accepts the fact that we're going to have some sort of excavator and haulage combined robot. I should never say that, of course. It's up to you to come up with some novel and innovative ways of moving the material around. And this is the kind of example that Jose's found for us here. Next slide, please. Looking at the extraction plant, the tailings, the transportation, the propellant production, the downstream aspects, I think one of the issues that's most important here is the resistance against dust, abrasion, and corrosion, and the robustness. Trying to keep it simple. We've got to keep everything as simple as possible to avoid complexity, because we're not in a position where we can get maintenance out there to solve any ongoing issues that we're going to have at the plant. And one thing that Jose pointed out, which I thought was really interesting, was the concept of heat rejection. How are we going to, if we're going to use some sort of heat to separate that ice away from the regolith, obviously under pressure, so it doesn't just sublime, we're going to have some sort of furnace or some sort of control area. How do we reject the heat from that? We don't have thermal heat radiation as an option in a vacuum. Next slide, please. I think that the dust and abrasion and corrosion, Jose has mentioned that again, and I think it becomes a critical issue because it is going to affect not only the operation of your equipment, but it also brings safety concerns, health concerns for anybody who's going to be around this area. And it's certainly an issue that was a concern in the previous efforts to explore the moon. And the last slide, please. The last slide just talks about the fact that mining the moon is it's a dream challenge, and I'm hoping that the many people on this call, for you're natural born problem solvers and true miners. That's what we want to see, and we're looking at this as a real exciting opportunity. It really does open up the business opportunity is some years away, but it is quite significant, and it's a very exciting opportunity for everybody. So once again, just a reminder, simplicity, easy maintenance. Those parts need to have a high lifespan. They need to be able to be resistant to abrasion. Anything that needs to be replaced needs to be able to be replaced on site. You cannot just deliver things on. There's no FedEx on the moon, I'm afraid. And the flexibility to work under different scenarios. And as Jerry mentioned, scalability is important. We're going to start small, but it needs to be something that that has a pathway to scalability and a pathway to an eventual fulfilling the role that we need in terms of providing the fuel for future missions going forward. That's all I have for you. Thanks very much.
Thanks so much, Phil. Really enjoyed that insight, and I really hope that these slides from Phil and Jerry will give you a really well-rounded perspective in terms of the objectives of this challenge and a little bit of background into how this fits into NASA's overall goals for greater space exploration. Now we'd like to answer some questions that we've received throughout this webinar. Oops, excuse me. And our first question asks about phase 2 in terms of when it opens and when the submission is due. That information is not available yet, but we should hopefully have an update on that shortly after the close of phase 1. We have a question about eligibility in terms of being able to participate at a certain age. I would like to note that you must be 18 years or older to participate. If you have any more questions about that, please read the eligibility requirements form, which spells that out in more detail. One more question about the eligibility documentation, whether a citizenship document such as a green card or passport copy is required. We don't need that. We ask you to self-certify your location and your citizenship status. So we do not need the copies of those documents. One question for our subject matter experts. It says that for the system architecture, data is required on the delivery of water to the site. The mobile platform. So I'm sorry, this is a bit of a loaded question. The mobile platform that was part of Watts on the Moon and is the vehicle presumably for this requirement. And in the performance analyses, there's a requirement for information on the mass of the NASA water extraction plant. That's also an element that was part of Watts on the Moon. The question is, in order to concentrate on the system architecture of the actual excavating processes, is it permissible to just reference this material from the challenge itself? I'm not sure who might be best to address that.
I know for sure that it's not me.
Hey, Adam, this is Ollie. Yeah, that's a question. I would say, I mean, I'm not the expert that this is derived at, but I would say, yes, this should be referenced in your materials so that you can be diligent with the amount of page space, because I think this is a question about limited page space. So reference that in your document. That, yes, that is what you should do. And then Adam, we had another question about, can you comment on how to submit documents? Should we email attachments and links to the admin email? So
sure. So if you are wishing to provide your eligibility forms, I provided the email address to send those to. And if you are referring to the submission itself, that is provided through the website under your login information on the breaktheicechallenge.com site.
Yeah, and just to say as clearly as possible. So there is a submission form. So you need to register for the challenge. And then once you go back into the challenge website, input your username, input your password. What will happen is a submit option will appear at the top of the screen. Click the submit button, and that will take you to the submission form. That submission form is how you enter this challenge. So do not email your submission to the admin email. There is a form that's designed that will be collecting all of your documents after you've registered.
Another question about the formatting for the submission. Can tables and figures use 10-point font? Yes, that's fine, but please make sure that text outside of figures and tables are adhering to the 12-point requirement. Another question, is there a Dropbox for all of these submission files? No, as I mentioned, the submission files are provided through the challenge website itself. And you'll see in the submission form exactly where you need to upload and provide specific inputs. Another question about the eligibility form. Can you please explain what exactly is the entity in the document? That's a great question. Entity refers to an organization that you would be competing on behalf of, as opposed to a solo competitor in which you're not competing under a specific company or a university or organization.
Hey, Adam, and then we have another question. Do we submit eligibility requirements under legal and other required documentation within the submission? Yes. So again, there's this form, the submission form, that has all of the required fields that you will need to submit into the phase 1 challenge. So we ask that you prepare and send the eligibility requirements so that essentially you can have assurance that you're eligible, but that will also be part of the submission form. So ideally you will have emailed that to us. We will have confirmed that you basically are eligible to compete in the challenge, and then you will also upload that as part of the submission, if that makes sense. So we will essentially have 2 copies of that document, or in the case that you have not emailed us this document yet, you will just upload it in the submission form. And then we will do the eligibility requirements as soon as we receive that document and begin processing the submissions. We have another question. What if a submission file is larger than what is typically allowed as an email attachment? So again, you're not emailing this to us. We do think that our form fields are able to intake and process larger documents than would be emailed. So we will be standing by to troubleshoot the form if there are documents that are very large, but in that case, it would not be emailed to us. So it would be, you would be inputting these forms in the submission form fields.
One question for our subject matter experts. Since there are no MTTF or MTBF for the moon usage, what do you think is the best way to see this?
I typed a quick answer to that. Basically, overall, we are looking at a total production amount over a minimum year of operation. So we expect the system to operate for at least a year. And whether the use of redundancy or maintenance or high reliability is utilized by the developers is it's open to each organization to consider, but that, you know, obviously the more maintenance that's required or the more redundancy will impact the overall initial and continuing mass and logistics associated with that particular concept. It's hard to define a mean time between failure when you actually don't have data on necessarily the parts that you're talking about.
Excellent. Thank you so much. Another question about the difference between competing as under individual versus entity within the eligibility requirements form. If a team is comprised of individual members, are they considered an entity? No. As I mentioned, unless that team is representing a specific entity, if it is just a handful of individuals from different organizations working as individuals that are not affiliated with an organization, then they are not considered an entity. Another question about eligibility. Do we submit eligibility requirements under legal and other required documentation within the submission? Yes. However, we do request that this documentation is emailed to us at info@breaktheicechallenge.com. That way we can review it and let you know if your form is compliant and you are eligible to compete. And you will need to provide that documentation when you are providing your submission as well.
And then we have some questions on how many teams are participating and how many teams have applied. So that information is not going to be shared until the end of the phase 1 judging period.
Should we upload our proof of insurance documentation in the submission in addition to emailing it? Yes. Where can we submit supporting documentation outside of the 25-page limit? These page limits are in place for a reason, and with these specific submission elements. So unfortunately, outside of these particular areas where you are providing submission elements, we can't submit any supplementary documentation. Does the cover page and table of contents count against the 15-page limit of the system architecture? I believe the answer to that is no. But I will double check and I can follow up on this question right after this. Another question about the system architecture. Can it be more than 25 pages? No. As I mentioned, there are page limits to many of these submission elements, and we will not be reviewing any material that exceeds these particular page limits. One question about the excavation plan, whether or not multiple PDF files can be provided here. No, we are accepting one PDF file that can be up to 5 pages.
And then we have a question, why would NASA not share how many teams are participating? So the answer is this is a live number. It's not like that this information is not existing. The phase 1 submission period has not closed. So this is not something that, we will know how many teams are participating at the close of the phase 1 submission period.
Please confirm that we do not need to send any proof of residency. Yes, I can confirm that. As I mentioned, you are required to self-certify your residency, and we do not need any passports or any similar residence and citizenship documentation. One question about overall hardware and similar solutions that Break the Ice is seeking. What resources exist for teams to be able to see other opportunities for similar hardware solutions? That's a really good question. If you, one great area to monitor is the SBIRs solicitations that offer grants for teams that provide solutions in specific categories and topic areas. Also, please be sure to follow the NASA challenges, which I can provide a link. I believe that link exists in one of the webinars. However, that information is very accessible, and there are many opportunities to participate outside of just this challenge. I would also like to add that this webinar has been recorded. It will be provided to all of our challenge registrants and those that have signed up for updates. We'll also make sure it's archived on the challenge website itself, and we'll also add it to our YouTube page.
Hey, Adam. So I think we have a final question and then we will likely wrap up because the questions are slowing down. So I think this says, how can we get notifications on NASA meetings, which are online? So one of the best ways to do this is first to follow NASA's social media pages if you want to get notifications across kind of the variety of mission areas. You should take a look at that. As it pertains to this specific challenge, you can sign up for progress updates. But in general, the best way if you want to be tracking notifications on NASA's activities is either by going to their website or by following them on social media. They have a very robust social media channels that they use across their mission priorities and programs. So that's probably the best way to get any notifications.
And one more question, unless a couple more sneak in here. And this is for our subject matter experts. Is the expectation that the landed mass will be a standalone lander capable of landing on the lunar surface on its own power, or a platform that will be brought to the surface and deployed by a third-party commercial lander? Jerry, can you take a stab at that?
For a full-scale system that I was talking about, it could be either, for that matter. We would look, most likely the landers will be commercial in nature unless there is an issue with packaging. I think the CLIPS landers at this point only have a limited payload capability of a few hundred kilograms. That could change over time as these activities develop. And as I mentioned, you know, there's a lot of discussion going on about the demonstrations in the pilot plants, who's going to do those and how. But we do see the full-scale implementation being done by a commercial organization. So if it is a commercial company that is going to mine the water and process it, they probably will turn to another company to land it and deploy it.
Great, thank you. Well, seeing that we have no more questions, I think this concludes our webinar. I would like to offer you the opportunity to continue asking questions either through the challenge website itself or email us at info@breaktheicechallenge.com. Once again, this recording will be provided, and we really look forward to receiving your submissions up and through June 18th. And thank you again for your participation today, and good luck on this challenge.